Hi everybody, welcome to another video in Calculus 3, section 17.3, conservative vector fields. Before we define a conservative vector fields, we need to define a few things. First, a simple closed curve. This is pretty straightforward. A curve is simple if it never intersects itself. The way we write that is, it just mathematically we define that not intersect itself like this. And the curve is closed if the initial and the terminal points are the same. So with that, this is closed. And it is also simple because it does not self-intersecting. It does not intersect in itself. This is not closed because the endpoints are not the same, but it's not intersecting itself. So not closed and simple. This one closed but not simple because it intersects itself. So this one is not simple because it intersects itself, and not closed because the endpoints are not the same. Right. And then we define a region. This is for region. That is for the curve which is on the outside, and the region which is in the inside, pretty much. So the region is connected if it is possible to connect any two points by a continuous curve lying entirely in R. So if we have 2 points here, we can go from here to there, and the curve is completely inside of the region. If we have 2 points like this, there's no way we can connect them without getting outside of the region R. Same thing here, we cannot connect them without getting outside the region. Here it's okay, we can connect them. Right. Next we define a simply connected region if there's no hole in it, pretty much the way we define. If there's no hole in it, when we have a curve like this, we can construct that into a single point. If we have a curve around a hole, when we try to construct that into a point, we cannot do that because it is a hole in it. The smallest we can get is a hole itself. Right, so that's just some terminology here. Now, more important, what we need is to know what is a vector field, or when a vector field is said to be conservative. So a vector field is said to be conservative if there exists a scalar function such that the vector field is equal to the gradient of the function. And that function is called a potential function. In that case, phi is called a potential function. And the key here is it is a potential function, so there's more than one. Just like the antiderivative, there are a bunch of them, different by constant. Right. So that definition is nice and all, but it's not a criteria to determine if the vector field is conservative or not. The way we know if a vector field is conservative, by the way, if the vector field is defined on the connected or simply connected region, has the first continuous and the vector field has component function. Those component functions have continuous first partial derivative, then it is conservative if this condition is satisfied. The way we memorize this, of course, it's not try to memorize it like this. Consider if we write like this, and this is just like determinant. So derivative of h with respect to y is equal to the derivative of z with respect to g, with g with respect to z. Derivative of h with respect to x is the same as derivative of f with respect to z, and derivative of g with respect to x equal derivative of y of f with respect to y. Yeah, so pretty much exactly from the determinant. Now if it is only a vector in R2, then those two are equal. Derivative of g with respect to x equal derivative of f with respect to y. Right? Of course, derivative of the function with respect to the variables. And then why do I switch this? Of course, when we go to section 17.5, it makes sense why we do like this. But yeah, it is come from a determinant. Right, next. A determinant whether the following vector fields are conservative on R2 or R3 respectively. Right, so when we look at this function, the first one is f, the second one is g. Right, so just going to write like that first, and then it is conservative if for two variables. It is conservative if derivative of g with respect to x is the same as derivative of f, derivative of the function with respect to y. So this is the criteria. So now we just take derivative of g with respect to x, or derivative of f with respect to y. Derivative of f with respect to y. Y is a constant. I mean, x is a constant, so we stay there. Derivative of cosine of y is negative sine y. So we have negative e to the x sine y. Now derivative of g with respect to x. Derivative of g with respect to x, y is a constant, so we have negative e to the x. Derivative of sine y is sine y is a constant. Yeah, we just take derivative with respect to x. Now those two are equal. Since derivative of f with respect to y is the same derivative of g with respect to x, so the vector field is conservative. So the vector field is conservative. So f is conservative. Right, simple enough. Right, next we have the function of three variables and the vector field in R3. I mean, we have three functions of three variables, f, g, and h. Right. So this is three variables x, y, and z, and three functions f, g, and h. So just like a determinant, first we need to verify number one, derivative of h with respect to y. Instead of write like that, I can also write using the subscript. Derivative of h with respect to y, is that the same as derivative of g with respect to z? So that's the first criteria. So derivative of h with respect to y is 2. And derivative of g with respect to z, that also 2. And are equal. So yes, that one's good. Next. Next we have derivative of h with respect to x, is that the same as derivative of f with respect to z. Right. Derivative of h with respect to x. Y is a constant. Derivative of x is 1, so we just have negative 2z. Derivative of f with respect to z. xy is constant. Derivative of negative 2z, negative z squared is negative 2z. Yes, they equal to. Equation number 3. Is derivative of g with respect to x is that equal to derivative of f with respect to y. So derivative of g with respect to x, that will be 2x. And derivative of f with respect to y, z is a constant, so we don't have, that doesn't matter. Derivative of 2xy with respect to y is 2x, and that equal also. So those three criteria are satisfied, so we say the vector field is conservative. Yeah, so just have to check this criteria, so pretty simple, right? So it works just like a determinant, right? So that's the first one, that's the second one, and that's the third one. Yeah. So right, next, find potential function for this conservative vector field. So now we did verify that this is a conservative vector field. Now, this technique is very important. You certainly will see this in Calc 3, what we're doing now. And you will see that at least differential equation and maybe many more math or science classes. Right. So find the potential function of this vector field. So first of all, once again, we have this f, and this is g. Now, we know that this one is conservative because this one is given that the vector field is conservative, and we did verify that it is conservative. So we will write, since I said the notation now is very important, that is the vector field f is conservative. That means, by definition, there exists a potential function such that there's the sixth potential function phi such that vector field f equal to the gradient of phi, meaning derivative of vector field f, meaning that we have the component equal to the partial derivative with respect to x with respect to y. Right? So the vector field equal to the gradient, then this is the gradient. Or we just write the next step, the next one we don't need to write all of that. We just say f equal to derivative of respect to x, and g equal to derivative with respect to y. So these two conditions, what we have. So if it is conservative, we're going to have those two, right? And we're trying to find the function, right? So the idea is, if we have the derivative, we're going to get back to the function. We do the antiderivative or finding the integral. So this is the first thing we will do. We integrate. So we start with and that is equal to f, which is e to the x cosine y. Now if the derivative equal to that, then we integrate we're going to get the function derivative, so we integrate. Of course we can start with this and we integrate with respect to y, but here derivative with respect to x. To undo it, we will integrate that function. With respect to x, to undo the derivative x here. Yeah. So if we have derivative with respect to x, we will integrate with respect to x to undo it. Get back to the function. Right. This is a function where x is variable, cosine of y is a constant. So integral of e to the x is e to the x, and then that constant. Now, because this one with respect to x, we can have a constant. But that constant with respect to x, we can have the constant function of y. So this is a constant with respect to x. We can write as a function of y. So this is constant with respect to x, because y in that case is just variable, or just a constant, because x is a variable. So we integrate. Now, if we have the function, now we will differentiate. So we will differentiate with respect to what? Now, we start with this condition. Now we'll differentiate so that we'll have this condition. So we will have derivative of this with respect to y. So first we integrate phi of x, integrate with respect to x. And then we differentiate with respect to y. Right, we take derivative of this with respect to y. Derivative of that is e to x is constant. Derivative of cosine y is negative sine y. And then derivative of this constant, of this with respect to y, is going to be derivative of c with respect to y. And we have to match this with g. So this column equal to, meaning we're going to make that equal to g. So we have e to the x negative e to the x sine y plus derivative of c with respect to y equal to g negative e to the x sine y. Now those two are equal. Can cross them out. So c prime of y is equal to 0. If that is equal to 0, that means the function is constant. So derivative equal to 0, meaning it has to be a constant. So now we know that it is a constant. All we need is to substitute this back into this, and we have the answer. So the potential function is equal to e to the x cosine y plus a constant. By the way, the question only asks for a potential function. So we can choose C to be 0 if that is one of the potential function, right? So we can choose the constant to be 0 if we just want a potential function, right? So that's the idea though. If it is conservative, then those equal to, and then we find that by integrate and then differentiate. If there are three variables, integrate, differentiate, integrate, and differentiate until we solve for that very constant. Right. Right. I'm sorry. The recording software crashed, so we have to restart again. Anyway, so we're trying to find the potential function for this vector field. We already know this is a conservative vector field and has three components. By the way, try to write small because this might take a lot of space. So first we know that it is conservative. So there exists a potential function. Just that the vector field is equal to the gradient of that function, meaning that the vector field, each component function is equal to the partial derivative right. And now just like the last one, we will take one and to integrate to undo the partial derivative, and we just keep doing that. So first we start with this f equal to phi of x, and so that equal to f, so this equal to 2xy minus z squared. So first we'll integrate. To get back to the function, this function of three variable x, y, z, we integrate with respect to the same variable. So we undo the derivative. Derivative of this is 2 derivative integrate of x with respect to x. Only x is variable, so x over 2 y, and then minus z squared. We stick an x to it because z is a constant, z squared is a constant. So we have x squared y minus z squared x. Because that plus a constant, right? So we have that plus there's a constant. Since we integrate with respect to x, the constant might be in terms of y and z. So which equal to what? X squared y minus z squared x plus c of y and z. Yeah, but just simplify the two here. So that is the potential function. We take that form. Now earlier we differentiate. Now we we integrate, now we differentiate. So we take the first one. Now next we're going to take derivative with respect to y. So that derivative of this with respect to y, just that, so be 2xy. Sorry, just x squared, right? Yeah, derivative of this with respect to y, so that is just x squared. That constant derivative is 0. That one have y in it, so we will have derivative of c. We take derivative with respect to y, so we have c of y. Right? So c has two derivative, two variables, so we're not going to write c prime. Previously, we just have the function of just one variable. When we take derivative, that's just a derivative. This one, two variables, so that partial derivative. And when so we take it derivative with respect to y, and we have to match that with g, make that equal to g. So which means x squared plus cy equal to g is x squared plus 2z. Right? Cancel the x squared. Just have 2z. So c's derivative of c with respect to y is 2z. So to get back to z, to c, we integrate. This is with respect to y. So if we derivative integrate with respect to z, never mind. Let's write that in the next line so we see it. Suddenly we integrate, right? Just keep doing. So from that, we differentiate. We integrate, but get back to C. Where's so C sub y equal to 2z. So C equal to integrate of 2z with respect to y. So that gives us 2yz. Now since we have this, we can put it back in that. So we have the function now is equal to x squared y minus z squared x, and the function is 2yz. And I forgot one more thing. We integrate with respect to y, and c is the function of y and z. So certainly we might still have the function of z. Sorry. We don't want to use d as a constant because d usually reserved for derivative. So we write that e of z. Yeah. So integrate this. That's what we have. So and now we have that. So this plus is of z. Right, so integrate, differentiate, integrate, and then we differentiate. One last step is to differentiate this, and we use this one. So we differentiate with respect to z. Derivative of this with respect to z, that constant, so we have negative 2xz plus 2y, and now derivative of e with respect to z. So that's just derivative, not partial derivative, because it is the function, only one variable. We will make this equal to h. So we have negative 2xz plus 2y plus e prime equal to h, 2y minus 2xz. Cancel out. E prime of z is a constant. E derivative is equal to 0, so e of z is a constant. And we substitute that back into that. So potential function equal to that x square y minus z square x 2yz plus constant. Yeah, that constant could be anything, or we can choose that to be 0. So essentially, first step is we use this. So first step is integrate with respect to x to undo this, get back to the function, and then we differentiate with respect to y. Second step, differentiate with respect to y, and we're going to make that equal to g. So that takes care of this equation. Why we do that? And we have the function g y of z, and then we integrate that function to get back to c. So integrate with respect to y, and then differentiate with respect to z to match that. Yeah, so those are the steps. So just integrate, and we have that constant function, and then we have to solve for that constant function with respect to x, and so we have to integrate, differentiate, integrate, differentiate, just switching between the two. Right. So that's what we have. Next, let f be a continuous. Now we have two fundamental theorem of linear algebra, because by the name of it, it is rather important. Right, so let f, by the way, I forgot, this is a typo here, this should be a vector field f. Let vector field f be a continuous vector field on an open connected region if there exists a potential function, which means vector field f is conservative if and only if the line integral equal to that. So this is like the fundamental theorem of calculus, but it is for line integral. Of course, when we write like this, we can also write as a function. Could be x, y, could be z, evaluate at a and b. Where a and b for any point, and C is a smooth oriented curve from A to B. So now, so here is an example. Evaluate this vector field. Evaluate this line integral when C is a simple curve from A to B. Right. By the way, there's a clue. Usually when we say evaluate the line integral on just a simple curve, and it's not specified, right? All we have is just it's between 2 points. If it is really matters, they have to specify, is that going to go like this, or they just go like this, or they go like that. All we know is different at the endpoints. We know that go from A to B. That's all we know. It did not specify any path, right? If it did not specify any path, that means all of the line integral would have to be the same. Otherwise, they have to specify in the question, right? Right. So we're going to do this in 2 different ways. First one, we're going to use the line segment from A to B. So a simple line integral. By the way, the line integral can be written as a vector field f dot dr. So the first step is to parameterize the curve C. Right? So C now for the line segment. So the first part of it, like I said, if it did not specify the curve from A to B, why don't we choose the line segment? That's probably the most direct and easiest solution. So first we're going to use the line segment from A to B, because this one did not specify, so we can just pick one, right? So from line segment A to B, the parameterization is R of t is equal to A plus t times the vector AB when t between 0 and 1. So that is the parameterization of the line, of a line segment. So here we have R of t equal to A plus t times the vector AB. A is that point, plus t, the vector AB is because it's B minus A, so AB is final minus initial. So we have the final 1, 2, 3 minus the point -3, -2, -1. So that gives us what? -3, -2, and -1. Vector 1 minus -3, so that is 4. 2 minus a -2, that is also 4. And 3 minus -1, that's also 4. So that add them together. I said the notation of vector doesn't really matter. They're the same. By the same, I mean they have 3 components. So -3 plus 4t, -2 plus 4t, and -1 plus 4t. T is between 0 and 1. So we're going to parameterize that. So with this, we have x equal to -3 plus 4t, y is that, and z is that. So x equal to -3 plus 4t, y -2 plus 4t, and z -2, -1 plus 4t. Right, so that's the first step, parameterize it. Meaning that we write x, y, z in terms of t. Now we can write the vector field f in terms of t. So vector field f equal to, I'm going to write those 3 components to x, y. This problem is a lot simpler in my head. Now we have to write this in terms of t, that x, y, and z. Oh. Right, so we're going to write that in terms of t. So, 2xy to choose 0, 0, 0. That saves a lot of time. Anyway, y negative 2 plus 4t minus z squared x squared plus 2z and then 2y. Oh, can even fit on one line. Great. Yeah, you know, we just substitute all of that x, y, z into that equation. So, seems very long. I'm not going to bother to simplify that. So that's the first step. So now, first step is parameterize, write everything in terms of t. Now we write f in terms of t. So let's just recap. So for line integral, that's the first step we do. Parameterize. Next, write that vector field in terms of t, and now we write dr in terms of t. Dr equal to derivative of r respect to t dt. Right, this is r of t, right? We're going to take derivative of this with respect to t. It's actually very easy, just 4, 4, and 4. dt. And finally, so we have everything in terms of t, and then the line integral equal to f in terms of t dot r prime t dt. So we just have all this dot with this vector dt. Right, so the integral with this time go from 0 to 1. I'm just going to write f of dot 4, 4, and 4 dt. Right. I'm just going to write all of this dot 4, 4, and 4. So when we do the dot product, the first one times 4, second one times 4, the last one times 4, just add all of them up. So that's very, very simple. Just extremely long in this problem. So first we have the first component times 4. So that gives us 8 minus 3 plus 4t minus 2 plus 4t and times 4. Then 1 plus 4t. That's the first one. Next, this components times 4. Let's say times 4, right? And then that component times 4. of that dt. So I'm going to pause the video and enter all of this in the calculator because that takes a lot of time. Right, we continue. If you wonder, it took me 5 minutes to enter all of that in the calculator. Right, so actually what I get to simplify things, enter the first bracket here in y1, second bracket in y2, and this bracket in y3. So those are 3 functions, 3 part of it. And now I just evaluate from 0 to 1, and I would just say y1 plus y2 plus y3. I can hit variable y function y1 plus, or to just hit alpha trace y2, or not, we just hit variable y variable function y3. All that 8. Right. Now, so that's the first part. I said from A to B, if the curve is not specified, we can just pick the line or the straight line from A to B. Now, next we're going to use the fundamental theorem of integrals, of line integral. First of all, previously we have the potential function for this vector field. So see previous example. See previous example. We have the potential function equal to this: x squared y minus z squared x plus 2yz, and we choose the one where c equal to 0, the constant equal to 0. So that's all we need. Just like in the definite integral, usually we just say the constant equal to 0. So by that fundamental theorem of line integrals, the line integral of a curve C is just equal to the potential function from A to B. So potential function is that. We evaluate from A, -3, -2, and -1. And from 1 to 3. So just like integral, we're going to put x, y, z into that, and then subtract, we put those into that. So first, 1 square times 2 minus 3 square times 1 plus 2 times 2 times 3. Then we subtract. Now we're going to put -3 square for x, y is -2, z is -1 square, x is -3 plus 2y z. So that is 2 minus 9 plus 12. Subtract -3, that's 9, so that minus 18 plus 3 plus 2. So that 2 minus 9, -7 plus 12 is 5. that is 14 minus 5, subtract negative 18, so that minus 13. Right, let me pause the video again and then let me check the math. Right, I found the error. I hate doing that, but so this is minus 2xz, x is 3, so this should be 3 there, and this should be 3, and once you do that, that gives us 16. Right, sorry about that. And when we do this, 2 times negative 2, so that is plus 4. So negative 18 plus 7, so that's negative 11. And the answer is also 16. Right. Yeah. Sorry about that. Just a bit tedious here. But bottom line is, when I apply integral, normally we just parameterize C, parameterize the curve, so that we have x, y, and z. Once we know that, substitute into a function, substitute into the vector field, and after that, dr is equal r prime t dt. So we take the derivative of this with respect to t, and then do the dot product. This is just extremely long. That integral is equal to 16. Or we use the fundamental theorem of applied integral. We just integrate, and instead of integrate, we found the we not integrate, but we find the potential function, which we did earlier. So that's what we have. And now just evaluate at those 2 points. So we substitute in. So that's what we have. Yeah, it's not that bad, but I just choose an example that is not as simple as it needs to. Right, now a little bit more details here, a little more theoretical idea here. Now, let F be a continuous vector field with the domain on. Then if the line integral are the same for any curve with the same initial and terminal points. So those two integrals are the same. But those two integrals are the same if they have the same initial, same terminal points. In that case, we call them independent path. So just like the last example we did, doesn't matter how do we go from A to B. We can go directly to A to B, or we can go any path. It doesn't matter. Those line integral will be equal to the same thing. But like I said, it doesn't work for all of them. There have to be some certain vector field that satisfy this condition. So for now, we define that to be independent path. Next, if the vector field F is continuous on the vector field, the line integral is independent of path, then it is conservative. So what we say is, if it is independent of path, then it is conservative. Notice that it is if and then, not if and only if, meaning that only go one direction. Right? So if it is conservative, that's different story. Right, next. Let R be in R2 or D in R3 on an open region, then F is conservative field if and only if the line integral equal to 0 on every closed, so the idea here is closed simple curve C in R. And finally, next we have all of them, all the equivalent. So So what the idea here? So the idea here is, let's say we go from A to B. Could be different paths, right? Let's say we do that over C1 and then C2. Now, it says that if it is conservative, then the line integral equal to 0 on a closed curve. So if the curve is closed, it's equal to 0. By the way, if it is a closed curve, we can write with a circle or the circulation. Right. So now how we tie all of this idea together. So first, it is, let's say this is C1, this is C2. C1 go in that direction and C2 go in that direction. So, first of all, they said that if this is equal to 0, now vector C is equal to, the curve C is go from A to B and go back to A, right? So in that case, we can say C is E1 minus C2. Why is that minus C2? Because C2 is going that direction. If you want to turn it back, well, if you want that to go this way, we have to turn that to subtract. So C1, C2. If we want to reverse that, we go C1 minus C2. So C is equal to that. Right. So let's just write the line integral. I'm not going to use the circle because now I'm going to split C1 minus C2. And that equal to C1 minus C2. So line integral of two parts C1 minus C2. So we do C1 first and then we minus the line integral on C2. Now, what kicks in says that if it is conservative, then it is independent of path. Because it is conservative, those two are the same because they are independent of path. So that's why this is equal to 0. That's why equal to 0. Now to tie everything together, we have this. Let F be a conservative vector field either in R2 or R3. Then we have these three are equivalent. There exists a potential function. And then fundamental theorem of line integral. So this one is independent of path. When we write like this, we mean it is independent of path. Doesn't matter how we go from A to B. It just matters that the endpoints, we start from A, we end at B. So this second condition here is independent of path. And if it is independent of path, as we show, then the line integral along any closed curve is equal to 0. Yeah, so those three conditions are equivalent if the vector field is conservative. Right? Once again, if it is conservative, then there's a potential function. And then if there's a potential function, it is independent of path. And if it is independent of path, then suddenly the line integral on every closed curve is equal to 0. Right. Now we do some exercise. Right, first, let's try to find the potential function. Again, determine if the vector field is conservative. If it is, find the potential function. Right. So that first part is f, this is g. Now if it is conservative, meaning that there's two variables x and y for two functions f and g, so it is conservative if we have derivative of g with respect to x is that equal to derivative of f with respect to y. So is that true? If it is conservative. So we take derivative of g with respect to x. Derivative of g with respect to x, this have to be a product rule. 2x times cosine of xy plus x squared, and derivative of this with respect to x, negative sine xy and then the chain rule times y. So that equal to 2x cosine of xy minus x squared y sine of xy. So that is derivative with respect of g with respect to x. Now we take derivative of f with respect to y. I might take a lot of space here. Derivative of f with respect to y, the first one is cosine of xy, and the chain rule, derivative of xy with respect to y, so that multiplied by x. And then next, derivative of this, that also a product rule, derivative of xy with respect to y, so this is x cosine xy, and then plus xy, derivative of cosine xy will be negative sine of xy with respect to y, so that's x. Or simplify this, we have x cosine xy, make it 2. And that minus x squared y sine of xy. So what we have here is this derivative with respect to y, g with f with respect to y, and then derivative of g with respect to x. They are the same, right? So they are equal. So yes, it is exact. I mean, there is the potential function. It is conservative. So if it is conservative, that means there exists a function so that partial derivative equal to f and g. So this condition is satisfied such that partial derivative with respect to x equal to f and partial derivative with respect to y equal to g. Right? So if it is conservative, that's what we have. Now, earlier, from here, then we say we're going to pick this on a big scheme of thing. We're going to start with this, we integrate, we get back to the function. So this is integrate with respect to x, we get back to the function. equal to something plus derivative of plus a function with respect to y, and then we differentiate with respect to y, and then we have that, and we're going to make that equal to g. So that's a big scheme of things. That's what we do. However, that function integrate with respect to x, that seems like a little bit of work, right? Because integrate this, we have integration by parts here with respect to x, and then pretty much it's just much longer. So instead of pick this, integrate with respect to x, we can just take this, integrate with respect to y. So we're using this instead. And now we integrate with respect to y. So that gives us the function integrate x squared cosine xy with respect to y. Yeah, because originally we have derivative with respect to y. So just do that. And this is just integral cosine is sine. And this is a constant times y. So we have sine of xy over x plus a constant with respect to y. So this is the function in terms of x. Which gives us x sine of xy plus c of x. Right, so integrate cosine is sine, and then we divide by that constant. So that pretty much like integrate of cosine of 5x, which is sine of 5x over that constant. Let's see. So now that constant is x because y is a variable. So we integrate the second one with respect to y, get back to the function. That's a lot better than integrating this. So we're integrating ready. Now check differentiate. Now we differentiate with respect to x. X sine xy, derivative of x is 1. We have sine of xy. And then plus x. Derivative of sine xy is cosine xy times derivative of inside with respect to x, so times y. So we have sine forget there's still a function. And so we start with this one, integrate to get back to the function. Now we differentiate and we match that with f. So we have sine of xy plus xy cosine xy plus c prime equal to f is that sine xy plus xy cosine xy. If that is equation, we can simplify that on both sides. So c prime is equal to 0. So with respect to x, there's no z here. So c is a constant. we just need to substitute back in here, and we have that. So the potential function equal to x sine of xy plus a constant. Right. So, right. It rather than take derivative of, integrate with respect to x to undo this to get back to the function. Rather do that, integrate f with respect to x to get back to the function, and then differentiate and match that to g. We do differently. We integrate with respect to y, and then differentiate and match that with f. So that certainly works. Right. By the way, if you have to integrate this with respect to x, if we integrate this with respect to x, we can split it and then integrate that. But this is integration by parts, so kind of complicated. So what we'll see here is, actually, we consider this sine of xy. Notice that note that the derivative of sine xy is equal to y cosine of xy. Right? So why is that important? That's important because here we have y cosine of xy. Now let's take a look at this problem again, but this time I'll write a little bit differently. 1 sine of xy, I will write 1 times sine of xy plus x times y cosine of xy dx. Note that what we have here is, if this is v, this will be v prime. If this is u, this is u prime. So in that, it is a product rule. Usually if we integrate a product, this is going to be just u times v, integral undo the derivative. So that's what we have. So the key here is we write that as a product rule, and the integral undo the derivative, and so that's what we have. So if we have to integrate that with respect to x, that's what we do. Yeah, split it and use substitution and then integration by parts. Yeah, that's not is the easiest one to do. Right. So that's what we have. So again, we can start with that, integrate f to get back to the function, and then differentiate and match that to g. So most of the problem we have integrate, differentiate. So that's usually the way it goes. Right. We have this function. Is this vector field conservative? F, G, and H. So when there are three variables, that is like the determinant. Oh, by the way, one more thing. Let's go back to this and say, why is this equal? And match that. When this equal, make it there's a sister potential function. This is actually not a proof or anything, but just a nice thing that we should notice. Right. So it says that here g of x equal f of y, right? Now it said if it is continuous, if it is conservative, then there exists a potential function, right? So that potential function derivative, so g of y is equal to g. So we have here, if there exists a potential function and f is that. What do we have here? This is yx, sorry. As we know already, the mixed partial derivative equal to 0, equal to each other. Derivative with respect to yx is the same as derivative with respect to xy. So that's why it makes sense, right? So this is important to note. That is the reason. If there is a potential function and they're equal, so it is conservative. So yeah, that's how they related to each other. Right. Now when we have three variables, three component functions, just use like the determinant. So we're going to check three things. First is derivative of h with respect to y the same as derivative of g with respect to z. Second is derivative of z of, just keep doing that. Derivative of h with respect to x is the same as derivative of f with respect to z. And then the third one is derivative of g with respect to x the same as derivative of f with respect to y. We need to track all three of them. But this function is easy, we just check that. So derivative of h with respect to y, that will be 0. And derivative of g with respect to z is also 0, so yes. Now derivative of x with respect to x, that's 0. Derivative of f with respect to z also 0, so yes. Derivative of g with respect to x is 1. Derivative of f with respect to y is 1, so yes, check. So all those three are check. F is conservative. Now if it is conservative, then there exists potential function such that derivative with respect to x equal to f, derivative of with respect to y equal to g, and with respect to z equal to h. Those three things. If it is conservative, those three things will work. So we start with this one. Actually, we can start with any of them. And then we will undo it. This derivative with respect to x, to undo it, we integrate with respect to x. Actually, we should start with this example first. Derivative with respect to x. So that just gives us xy, right? Because y is a constant with respect to x. Plus, now we have the constant. This with respect to x, integrate with respect to x, we might have y and z in it. Right, so integrate this to undo the derivative with respect to x. Now we will differentiate with something else. So we took care of that, so we're not going to use that anymore. So we have to use either one of this. So either we're going to take the derivative with respect to z, we make that equal to h, or we take the derivative of g and take the derivative of this with y and make that equal to g. So I'm going to actually go with the second one here. So we'll take the derivative with respect to y, it will be x plus derivative of yz. Now remember there are two variables with respect to y, so I have to be partial derivative. And I'm going to make that equal to g, which is x. So we have x plus cy of yz equal to g, which is just x. So x and x cancel out, so g of yz, this is constant. I mean, it is equal to 0. Right? X and x cancel out, this has to be 0. Now if it is 0, we can just integrate, get back to c of yz. If the derivative equal to 0, then it must be constant. And this constant is with respect to, so we integrate this with respect to y, so this constant might have z in it. Right? Yeah. So just integral of 0 with respect to y, so the answer may be a constant, but that constant depends on z. As long as we don't have y in it, it is fine. It could be any function of z. And then I will substitute this. So we have the function equal to xy plus the function in terms of z. We're not done, so we use those two. Now one more thing, we will take the derivative of this with respect to z. So integrate and now differentiate with respect to z. xy is a constant, derivative of that is 0, so we just have derivative of e with respect to z, and we will make this equal to h. So we have derivative with respect to z equal to h, which is 5. If it is 5, then the function is going to be equal to 5x plus a constant. That is our answer. If we substitute this back into this form, we have the potential function. So it's simple now, right? So first we check it is conservative. So now if it is conservative, the derivative of that potential function with respect to x equal to f, with respect to y equal to g, and with respect to z equal to h. And then we just pick one, integrate with respect to x, we undo it, get back to the function. Since this with respect to x, we might have y and z in it. So that's what the function look like. We take the derivative. Now we go to second one with respect to y, and we will make that equal to g. And g is equal to x, so we solve that. We have the constant with respect to y equal to 0. If the function with respect to y equal to 0, and so it must be, if the derivative equal to 0, it must be constant. But this constant with respect to y, so that might have z in it. And then so we substitute that back into this form, and then we differentiate with respect to z, and we make that equal to h. So we will solve for it. If we know the derivative, we can integrate, and so that's what we have. So that is a potential function, a potential function, because I choose the constant to be 0 if you want to. Right. Next, we only have that much space if we're going to do that line integral. it's not going to be enough. So we have to be clever here. So that is the function, potential function, right? So first of all, since f equal to the gradient of this function, what does that mean? If it has a potential function, it's certainly conservative, right? If it has the potential function, then when we go to the second partial derivative, where's that? Okay. If it has a potential function, then we take the partial derivative, a second order partial derivative, if its mixed partial derivative are equal. So we have this already, right? So the potential function is a potential function of f. Yeah, because it's the vector field equal to the gradient of some function. So that function is the potential function. And if there's a potential function, then what do we have? And notice that this curve, if you put 0 for t, and if we put 2 pi for t, those two will be the same. So what we have here is a closed curve. Because the endpoints are the same. Now if the endpoints are the same, this is on the closed curve, so we just say on the closed curve will be equal to what? Don't need to do anything. So why is that? So that's what we have, those theorem. First of all, there exists a potential function, right? If there exists a potential function, it doesn't matter then doesn't matter the path. From go from A to B, it could be E equal, doesn't matter the path, only depends on the endpoint. And now if we have 2 points, we go this route is the same as on this round. So the integral, those two integral will be the same. So this is C1, this is C2. So the line integral on C1 equal to the line integral on C2. Because there's a potential function, it is independent of path. So this path is the same as that path. The line integral on those paths. Next. See, we have those two. If we reverse the direction of the curve, we have negative. So that means we go this route is positive, and then minus that direction, we go back to the same. So in that case, if we want to go in the curve C1 and then minus C2, we go one complete revolution. Not complete revolution, one complete curve. So positive that way and negative the other way. So if we want to go like that, get back to the same point, that equal to 0. So if there is a potential function, fundamental theorem of line integral says it's independent of path. And if it's independent of path, then we can go one direction, two directions will be the same. If we reverse one of them, positive and then negative, that's why it is equal to 0. Right, so that's why we have to do much on that problem. Right, now we have another example here. Find the line integral for the curve in the parabolic segment y equal to x squared from 1, 1 to 2 and 4. 1, 1, 2 and 4. So we're talking about this. Right. So first is parameterize the vector, parameterize C. Parameterize C. Y equal to x squared, right? So why don't we let x equal to t, and then y will be t squared. So that's easy. X equal to t, y equal to t squared, because y equal to x squared. And t go from 1 to 2. So yes, we have the parameterization of t, of the curve C, sorry. So in that case, x equal to t and y equal to t squared. So that's the first step, parameterize C. Next, we write the vector field in terms of t. Y is t squared, so this is t squared squared. X is t, y is t squared. T to the 4th, 2t cubed. And then we're going to write dr in terms of t as well. So dr is r prime dt. So the reason of that is very simple. We have r of t, right? If we take derivative with respect to t, the notation for derivative is this. And then we just move the dt over. So that's what we have. So derivative of r, which is here, 1 and 2t. Don't forget there's dt. Right, so we have everything for the line integral. So that's a typical line integral problem. We can write f in terms of t dot that integral here from 1 to 2. So we have integral from 1 to 2, t to the 4th, 2t cubed, dot with 1 and 2t dt. So dot product t is 4 to the 4 times 1 and 2t cubed times 2t. That's 4t to the 4th power. So we have 5t to the 4th power dt. Right, so that's simple enough. If we type that correctly, we have 31. Right? So that is, we integrate we do the line integral, parameterize the curve, write the vector field, and dr in terms of t dot worked, integrate. That's simple enough. Next, find potential function. Now, if a question asks you to find potential function, we assume that it is conservative and there exists a potential function. So, find potential function in that case, meaning that derivative with respect to x is equal to f, and derivative with respect to y equal to g. So the vector field y squared to xy. So f is y squared and g is to xy. Right, it's ready. Now we can just find the potential function. Easy enough, we can just pick one or the other. Let's start with that. That equal to y squared. Now to get back to the function, we have to integrate with respect to x. Get back to the function. Integrate y squared with respect to x. With respect to xy squared is constant, so we have xy squared plus the constant with respect to y. Because we integrate with respect to x, everything have y in it. Everything has y in it will be a constant. Alright, so we took care of the first one. Then we'll take derivative with respect to y. From here, we have x times 2y plus derivative with respect to y. This is just derivative, not partial derivative, because the function only has one variable, which is 2xy, and we're going to make that equal to g. So 2xy c prime equal to g, which is 2xy. 2xy cancel out, so c prime of y equal to 0. So c of y must be a constant. Now if it is a constant, substitute that back. C of y, we will have the potential function. Right. Yeah. If we just want a potential function, we can choose the constant to be 0. But if we want to be more general form, we say that just plus a constant. Right, so that's good. Next, I'll find the line integral for the curve C for the line segment. Now, before doing that, what your answer will be? We certainly will do this. However, the answer has to be equal to 31. Why is that? Because there is the potential function. That means between those 2 points, the path is not really important. We can go from there to there. The line integral should be the same. So whether it is the parabolic segment or the straight line, that should be equal to 31. So we know the answer already. Just make sure we have that. So this time though, we actually just do the line integral, even though we know the answer is 31 already. Because there is a potential function. If there is no potential function, we cannot just do for the line segment, we have to go with the specific path. So if on the test, I'm not going to, probably you don't have that question on the test, but if I said from this point and to that point and you go on that path, then you see that if I give you the path is extremely complicated, then you probably think that if the function is potential, it will be much better if we just, if the vector field is conservative, then it is independent of path. So instead of go with the weird parameterization, we just use a straight line. Right. So here, we're going to just do the line segment here to confirm that the answer is equal to the same thing. So parameterize C, the C between 2 points. So RT equal to A plus TAB, where T between 0 and 1. Vector AB is B minus A, 2 minus 1, 4 minus 2. Four minus 1, right? So 3, 1 and 3. So we have the point 1 and 1, T 1 and 3. So that gives us 1 plus T and 1 plus 3T. That is the parameterization of T. The curve C in terms of T, sorry. Of course, from here we can say x equal to 1 plus T and y equal to 1 plus 3T. So that's the first step, we parameterize the curve. Next, now we know x and y in terms of T, we'll rewrite the vector field y squared to xy in terms of T. Y squared to xy. And then we can also write dr in terms of T. Derivative of this with respect to T, 1 and 3. dt. Right, now we have everything for the line integral. Write f in terms of T dot that in terms of T go from 0 to 1. So we have this vector field dot with this vector. So dot product give us multiply that times 1 and multiply that times 3. Give us 6, 1 plus T, 1 plus 3T. Now we integrate that. One plus 3T square plus 6 1 plus t 1 plus 3t right, good. That means we don't have to pause the video and check for the path, because there is, as mentioned before, there is a potential function. If there is a potential function, that means it is independent path from this point to that point where there is a parabolic path or where there is a line segment. We still have the same thing. It just shows that. So not only is these two paths in general, since we know this is independent path, we can say on the line integral only depends on the endpoint. Potential function from A to B. Potential function is xy squared, or from 1, 1 to 2, 4. So it's easy. Put 2 and 4 in. And then put 1 and 1 in. 32 minus 1 is 31. Right. So if there's a potential function, then we just use that potential function, evaluate at the endpoint and subtract. The path is not really matter if there's a potential function. Right. And then it actually shows that whether we will use the parabolic path on the line segment, we have the same thing, because that's what we're supposed to, because this is independent path. So yeah, I hope this last example you see the connection between them. Once again, if there's a potential function, then it's conservative and there's independent path. And also if it is independent path, the integral around a closed curve equal to 0 if it is independent path. So all of those ideas connected together: conservative, their potential function, independent path, line integral on a closed curve is equal to 0. Yep, so those 4 things connect. 4 things are equivalent to each other, except for tiny little things that, remember the theorem, when we write out, it have to be defined on a simple closed curve, and the region have to be simply connected. So all of the little details, yeah. So other than all the fine prints, those 4 things are equal. Conservative, there is a potential function, independent of path, and in line integral on the closed curve is equal to 0. So those 4 things are equivalent. If some small things are satisfied, but like I said, at this level we're not worried about those little fine prints. Right. So those 4 things are very important. Of course, also important is how do we find the potential function. That's also important. So find potential function, just integrate and differentiate, integrate, differentiate. Make sure that we satisfy every condition there. Right. With that, I then stop the video here. As always, thank you for watching.